Hey there, this is MathCamp321, and in this lesson, I'm going to show you how to find volumes of revolution using what's called the washer method. So, in the video from last night, we learned something called the disk method for finding volumes, but this is going to be a little bit different. So the first question we're going to address is, when do we use this thing called the washer method? So, let's take a look at the second sentence right here. If, when drawing the representative rectangles, you pass through an empty region, we're going to use what's called the washer method. And the formula that we're going to use is volume equals pi times the definite integral of big R squared minus little r squared from a to b, where big R is the outer radius and little r is the inner radius. Let's take a look at an example, and I think a lot of this will make a lot more sense. Number one, find the volume of the solid formed when the region determined by f of x equals x and g of x equals x squared are revolved about the x-axis. So f of x equals x is just going to be a line, and g of x equaling x squared is just going to be a parabola. And I've gone ahead and drawn those in for you. And I notice that there are 2 points of intersection. To know specifically where these two graphs cross, I'm going to set their functions equal to each other. So I'm going to say that x squared equals x. Because this is a quadratic, I'm going to set everything equal to 0, getting the x squared minus x equals 0. I'll factor out an x, leaving me with x times x minus 1 equals 0. And then I'll set each factor equal to 0, getting me x equals 0 and x equals 1. Now when I plug a 0 into either of these functions, the output is 0. So we have our first point of intersection at 0, 0. And when I plug 1 into either of these functions, I get the output 1. So this point up here is 1, 1. Now our objective is to revolve this region enclosed by these two curves about the x-axis. So I'm going to go ahead and shade in the x-axis just so we have a sense of what we're revolving around. And I'm going to draw that little loop to indicate the direction that we're rotating. Now, the first thing I need to do is imagine if I were to revolve this about the x-axis, we're going to have an outer radius and an inner radius. And the outer radius I'm going to draw with red, and I'm going to start by placing my pen tip on the x-axis. And I'm going to extend outward until I get to the farthest curve. And I'm going to call this point xy. So I'm going to call this x comma f of x. And now I'm going to clearly state what my outer radius is. So to get to this point here, we're going to go over x, and then we're going to go up f of x. So our outer radius is f of x. And I also want to make it clear that to get to this outermost point, I went through what I would consider to be an empty region where there's no graph at all. Like this little region right here is not part of the enclosed region, so it's the empty space. Now I need to identify the inner radius. So once again, with my green pen this time, I'm going to put my green pen on the axis of revolution, or the x-axis, and this time I'm going to project upward to the nearer of the two curves. And this curve is the parabola, or the g of x. So I'm going to think of this point as x comma g of x. And now I'm going to clearly state the smaller radius, or little r. So this green segment has a length determined by the fact that we're going to start at the origin, we're going to go over x, and then we're going to go up g of x. So our smaller radius is going to be g of x. And now I'm going to insert these parameters into the volume formula. So we're going to start off with a pi. Now another thing to mention is the fact that our representative rectangles, or the red and green lines that I drew in, are each perpendicular to the x-axis, which makes this a dx problem. Another way you could think about it is the fact that our axis of revolution is horizontal. So this is going to be a dx problem, and that means this is going to be a low x, and up here is going to be a high x. Now our low x is 0 because of this, and our high x is 1. Now the formula tells us to take the outer radius, or capital R, and then square it. And then from that, we're going to subtract, and we're going to subtract the smaller radius, which is g of x squared. And for the purpose of this video, we're just going to set up these definite integrals, and then we'll solve them tomorrow in class. So this is the definite integral, which would represent the volume of this enclosed region if revolved around the x-axis. Let's go on to another example. In our second example, we're asked to find the volume of the solid formed when the region determined by f of x equals x and g of x equals x squared are this time revolved around the line y equals -1. So the two functions that they start off with are exactly the same as in the first sample. So we already know that one is a line and the other is a parabola, and we know where they intersect. What's different though is the axis of revolution. This time the axis of revolution is not the x-axis, but it's the line y equals -1. So I'm going to go ahead and draw that in, and I'm actually going to make it blue, and then I'll put one of these little rotational arrows to show that I'm revolving about that line. Now the next thing that I need to do is figure out my representative rectangles, which will illustrate the outer radius, capital R, and the inner radius, lowercase r. So I'll start with the red, the outer radius, and I'm going to place my red pen on the axis of revolution, so way down here, and I'm going to project up until I get to the farthest curve. And I'm going to put a point here, and this will be x comma f of x. To establish what this outer radius is, it's slightly more challenging than in example number 1. If I start at the origin, which is over here, and I go over and then up, this little piece right here that I'm going to make a little bit thicker, this represents f of x. But if I start way down here on the axis of revolution, we have to add 1 to that. So it's going to be 1 unit from here to here, and then on top of that 1, we're going to add on f of x. So our outer radius is 1 plus f of x. Now let's figure out the inner radius. The inner radius, I'm going to again place this time my green pen on the axis of revolution, and I'm going to project up until I get to the nearer of the two curves. So we've got a far curve and a near curve. And this point I'm going to call x comma g of x. Now I'm going to place my green pen at the origin, and to get to that green point I'm going to travel over x and up g of x. So this little segment here, which I'm making thicker, this is the g of x. But the full length of the green segment starts down here at the axis of revolution. And from here to here, the thin portion of the green line is 1, and then on top of that is the g of x. So our inner radius is going to be 1 plus g of x. And to be very clear, this lower portion has a length of 1, and this upper portion has a length that's g of x. So we had to add them together to get this full inner radius. Let's now set up the volume. Now each of these lines is perpendicular to the x-axis, which makes this a dx problem. My lowest x that I see is 0, and that comes from here. And my high x is a 1, and that comes from there. And now I need to write an expression for the outer radius, which is the red, but then I need to square it, and then from it I need to subtract the inner radius, which will be green, and that's 1 plus g of x squared. So this definite integral gives the volume of the region shown if revolved about the line y equals -1. Let's take a look at a third example.